We are now ready to work out the potentials and fields of a moving charge that carries charge q and is moving with a velocity v. So, this lecture is going to be on scalar and vector potential of moving charges. Recall that in one previous lecture I had obtained the solution for a uniformly moving charge. Here we are doing it in general. So, we are taking a V t. So, this is not necessarily uniform, but includes uniformly moving charge, and this will give us the general potentials which are known as Reynard potentials. So, consider a charge q moving with some velocity v t. What we want to do is apply our formula that the scalar potential phi r t is given as integral 1 over 4 pi epsilon 0 rho r prime t retarded over r minus r prime t retarded d v prime. And similarly, the vector potential A r t is given as mu 0 over 4 pi integral j r prime at t retarded over r minus r prime at t retarded d v prime. Let me remind you that t retarded is equal to t minus mod r minus r prime itself at t retarded over c. And in the problems that we have solved so far, we could expand r prime in terms of t retarded and then keep only some important orders. However, that will be difficult here to do. So, first temptation of writing the solution would be that phi r t is equal to 1 over 4 pi epsilon 0 q divided by r minus r prime t retarded. And similarly, A r t will be equal to mu 0 over 4 pi q v at time retarded divided by r minus r prime at t retarded. This is a solution we had obtained earlier for slowly moving charges. So, this is something we would say could be the solution, but this is not. There is a correction factor. So, let me write that first and then we will talk about it. So, the correct solution is phi r t equals, this part remains 1 over 4 pi epsilon 0 q over square root of r minus r prime t retarded, and there is a correction factor which is 1 over 1 minus v at t retarded dot n, and same correction for A. Where n is this unit vector r minus r prime divided by modulus r minus r prime. Let me rewrite this on the next slide and then we can discuss it more. So, what we are saying is that if there is this charge q moving with velocity v, the scalar potential phi r t is equal to 1 over 4 pi epsilon 0 q over r minus r prime at t retarded, that is the position of the particle. To be better placed, let me write this as r naught at t retarded, so that indicates the position of the particle, and multiplied by this factor which is 1 over 1 minus v at t retarded dot n, where n is equal to r minus r naught t retarded divided by this modulus. So, it is that unit vector in that direction. And similarly, A r t is going to be mu 0 over 4 pi q v at t retarded divided by modulus r minus r naught at t retarded times this correction factor 1 minus v at t retarded dot n. And we want to know why this correction factor arises. To motivate this, I make two comments. Number one, Maxwell's theory is in terms of densities and current densities. So, in fact, point charge has a density q delta r, and if it is moving, its current density is q v delta r. And we got to take appropriate limits for this. So, what a point particle represents, this is a point particle, it represents limit of a distribution whose width is going to 0. Similarly, this current density actually represents this distribution moving with velocity v, and I got to take this limit d going to 0. But the moment you take this distribution and it is moving, you will see that this correction factor arises naturally. So, now that is my point number 2. A moving object looks either longer or shorter than its length. And why does that happen? Let us see. Suppose I have a rod and I am looking at it on one side and it is moving towards me. Suppose the light from the front end reaches my eye when the front end was at a distance L from the eye. So, it left the front end and reached my eye. It will take time L over c. If at the same time light pulse from the back end also left, it will take a time L plus L over C, where small l is the length of the rod. And you will see that it will not reach my eyes. So, the two light pulses will not reach simultaneously my eye. Now, length is measured by looking at the two ends simultaneously. So, this pulse is starting from the back end is falling short. So, what it has to do is leave a little earlier. So, here is this eye, here is the rod, the pulse from the front end left when this was at a distance L. However, the light from the back end has to leave a little earlier. So that although it covers a little longer distance, but it reaches the eye at the right time. Earlier it was taking a little longer. So, if it leaves little earlier, let us say by time delta t. What is the condition? Condition is that this light pulse should reach the front end when light pulse starts from here. So that what we have is that L plus V delta t, this is the whole distance when the light left, this is this distance, should be the same as L over C plus delta t. This is the time it took to reach the eye, so that they reach simultaneously times C. These two distances must be the same. I can also look at it from another point of view. We also said that the light should reach the front end when the pulse from the front end leaves, then we should also have that L plus V delta t over C is equal to, that is the time taken to reach the front end should be equal to delta t. Both these equations, whether I look at the first equation or the second equation, give me delta t equals L over C divided by 1 minus V over C. That means, if the light left a little earlier, it will reach my eyes simultaneously. I should have been slightly more careful in making this picture, which I made here. Let me explain this a bit. See, what we made was, when this rod was there and I was looking at it from here, the time taken was L over C if the light left the front end. From the back end, the time would have been L plus L over C. So, it was taking longer. So, if they left simultaneously, distance wise it will fall short. So, it has to leave a little earlier. I made these vertical dashed lines, which may confuse you from the point of view of time. This actually are showing the distance. So, it falls short of reaching the eye. So, if it left earlier, it would reach there, it will cover that distance. So, through this, what we have found is that when this rod is moving towards the eye, it would appear a little longer, because the distance would look to be L plus V delta t, which will be L plus V delta t has come out to be L over C divided by 1 minus V over C. So, this comes out to be L over 1 minus V over C greater than L. On the other hand, if the rod was moving the other way, it will appear shorter by L over 1 plus V over C, which is less than L. So, apparent length of the rod is shorter or longer, it basically changes if it is moving. What about at an angle? Suppose I was observing this rod from an angle, then the distance between the front end and the rear end would be L cos theta difference. And I will leave it for you to work out that in this case, the apparent length comes out to be L over 1 minus V over C cosine of theta, or plus V over C cosine of theta, depending on the direction of motion. Similarly, if I look at this distribution of charge, because now the light would be starting from the front end and the back end light would be starting from little behind, I will see more charge than the actual. If the charge distribution is moving towards me. So, it is moving like this with velocity v. If it is at an angle, then also it will look more, but it will be more like 1 over v over c cos theta factor. So, q apparent will be equal to q over 1 minus v over c cosine of theta. So, I would see the charge to be a little larger or a little smaller than the actual charge, and that will change the potential. Let us see it mathematically, so that we can apply it to derive our potentials. So, suppose I have this rod. To find its length, I am going to integrate a function f x prime t prime dx prime, where f x prime t prime is equal to 1 when x prime is over the rod, and it is 0 otherwise. So, given a t prime, some t prime, integration f x prime t prime dx prime will be equal to L, the actual length. But now, let us see what happens if t prime depends on x prime. That is, I am doing an integral of f x prime t minus x prime. Here I do not have to put mod, because it is one dimensional, over c dx prime, where this is t retarded is equal to t minus x x prime also is being calculated at t retarded divided by c. Now, this becomes a difficult integral to do, because t retarded depends on x prime. Makes integral difficult. So, we are going to do some mathematical trick, particularly because I know that integral f x prime t prime for a given t prime is equal to L. So, I somehow want to bring in this f x prime t prime into my mathematical tricks. So, let us see what am I doing. I am after this integral f x prime t retarded dx prime, and I am going to write this as integral f x prime t prime multiplied by delta function t prime minus t retarded dx prime dt prime. I am making it a little more complicated, but you will see the advantage. And I am going to switch the time integrals and x prime integrals and write this dt prime delta of t prime minus t retarded times integral dx prime f x prime t prime. That is my apparent length. Now, delta of t prime minus t retarded is equal to delta of t prime minus t minus x prime over c. By the way, you may be wondering what is x. X is the observation point. And this will be plus. And this is going to be equal to delta of t prime minus whatever this retarded time comes out to be divided by modulus of d is t prime minus t plus x prime over c over dt prime at this t retarded. So, what I have made use of is that delta of f x is equal to summation I delta x minus x I over df over d x at x I. Now, we have been given that this f t prime is equal to t prime minus t plus x prime over c. So, df dt prime is equal to 1 minus x prime dot over c, which is nothing but 1 minus v t prime over c. X prime after all depends on t prime. So, this integral dt prime delta of t prime minus t retarded integral dx prime f x prime t prime is going to be, notice that this part is for a given t prime, and for a given t prime this is equal to L, and rest of the complication is coming into this delta function, and when I integrate this is going to be nothing but divided by 1 minus v t prime over c t prime equals t retarded. This is the apparent length. So, we have done a trick where I calculate the integral of f function for a given t prime, and then rest of the complication of how t prime and t retarded and everything comes into the picture is taken into the delta function. Now, I am going to do exactly the same thing for the charge distributions. So, for a moving charge which is q, moving with velocity v t, I have rho r t equals q delta of r minus this r naught t, where r naught gives the position of the charge, and j r t equals q v at t delta of r minus r naught t, and phi r t is equal to 1 over 4 pi epsilon 0 integration of q delta r minus r naught t retarded divided by r minus r naught t retarded d should be prime dv prime. Keep in mind this delta function is a limit of this distribution going to 0, and therefore, I need to be careful while calculating this integral, because I am after all taking a density and taking its limit. So, again we do the same trick as earlier. What we do is write this as phi r t equals 1 over 4 pi epsilon 0 integral d t prime delta of t prime minus t retarded, then integral d v prime q delta r prime minus r naught at t prime divided by r minus r naught at t prime. Now, you see this t prime is given, is some given time t prime is a given time fixed, it is not changing with r prime. So, I can do this integral. When I do this integral, what do I get? I get this whole thing equal to 1 over 4 pi epsilon 0 integral d t prime delta of t prime minus t retarded, q will come out now, divided by r minus r naught t prime. T prime minus t retarded is equal to t prime minus t plus modulus of r minus r naught t prime over c, and the delta function delta t prime minus t retarded is going to be equal to, because of this whole thing, t retarded is determined by this being equal to 0. So, this is going to be equal to delta of t prime minus t retarded divided by this df by dt prime modulus. Let me explain this further. So, what I have is phi r t equals q over 4 pi epsilon 0 integral d t prime delta of t prime minus t retarded divided by r minus r naught t retarded, where t retarded is determined by t retarded is equal to t minus r naught at t retarded divided by c, or this is determined by t prime minus t plus r minus r prime at t prime divided by c being 0. So, this gives you the 0 of delta function, right. This is 0 at t prime equals t r. implies t prime equals t r. So, this is a function, and therefore, delta of t prime minus t plus r minus r prime r naught at t prime divided by c is going to be delta t prime minus t retarded, which is the solution of this equation that I just wrote, divided by d by dt prime of t prime minus t plus r minus r naught t prime divided by c at t retarded. Let us calculate that differential. D by dt prime of t prime minus t plus r minus r naught t prime divided by c is going to be equal to 1 minus one over c d by dt prime of r dot r, I am writing it vectorially just to be explicit, plus r naught dot r naught, and this is a function of t prime, minus 2 r dot r naught function of t prime raised to 1 half. And this comes out to be 1 plus 1 over c divided by 2 mod r minus r naught t retarded, because this is being calculated t retarded, and on top r is independent of t. So, you get 2 r naught dot r naught time derivative minus r dot r naught time derivative. So, let us see what we have done on the next slide. We are calculating phi r t, which we have reduced to q over 4 pi epsilon 0 integration d t prime delta of t prime minus t plus r minus r naught t prime divided by c divided by r minus r naught t prime, and we have found that when I take this f t prime to be equal to t prime minus t plus r minus r naught t divided by c, I get d f over d t prime at t retarded to be equal to 1 plus 1 over 2 c 2 r naught dot r naught derivative with respect to time minus r dot r naught derivative with respect to time divided by modulus r minus r naught. This 2 cancels, and I can switch the signs and write this as 1 minus r naught dot dotted with r minus r naught vector divided by modulus of r minus r naught, which is nothing but divided by c. 1 minus v at t retarded over c dotted with n, where n clearly is the unit vector from the retarded position of the charge to the observation point. So, if this particle is moving like this, here is the charged particle, and I am observing the potential at r this point at time t. The retarded position of this particle is somewhere behind, this is at time t here, then n is going to be unit vector in this direction. Let me make it thicker. This is n. This is from the retarded position, and the distance r minus r naught is this retarded position. This is modulus r minus r naught t retarded. And we have already written that t retarded is determined by this. T retarded is equal to t minus r naught t retarded divided by c. So, once I have gotten this factor, then it is very easy to write the potential, and is going to be phi r t equals q over 4 pi epsilon 0 1 over mod r minus r naught at t retarded times this factor 1 over 1 minus v at t retarded over c dot n, where n is the vector r minus r naught t retarded divided by r minus r naught distance. If I take r vector to be r minus r naught t retarded, I can also write my phi r t as equal to q over 4 pi epsilon 0 1 over r minus r dot v over c, all calculated at retarded time. This is how you see this formula in the books. In the same manner, exactly the same manner, now I can write A R t is equal to q v retarded mu 0 over 4 pi in front divided by r minus r dot v over c, all calculated at retarded time. So, we have now gotten this correction factor because of this moving charge. This is a beautiful way of looking at it, although we have been doing it, that any moving object looks longer. In the case of moving charges, what you see is, suppose there is a distribution of charge moving, and I am observing at this middle point somewhere. What I observe is the information collected by a light sphere coming in. So, suppose there is this light sphere which is closing in and bringing information to this observation point. Whatever information this light collects is the information that I see about the potential. If this charge distribution is moving towards me, even at an angle, I will collect more information, I will see it longer. If it is moving away from me, the incoming light sees it much less than when it was stationary. So, I see less of charge. That is the physical way of looking at it. Whatever you see coming from a charge or charge distribution is basically coming to you at speed of light. So, the speed of light sphere coming in is gathering information about the charge and bringing it to you. If the charge distribution is moving, you see it either longer or shorter or more charge or less charge, and that is what brings in this factor that we just saw. I should also enclose this. So, what we have gotten is that due to a moving charge, the scalar potential is q over 4 pi epsilon 0 1 over r minus v over c dot r, all calculated at t retarded, and the vector potential R t is equal to mu 0 over 4 pi q v t divided by r minus v t over c dot r, again calculated at t retarded. This is also a t retarded, where t retarded is determined by t retarded is equal to t minus r naught t retarded divided by c. And we have also seen how this is physically interpreted. How this is physically interpreted is that moving charge distribution has apparently total charge different from its actual charge, and that is shown by this factor of 1 over 1 minus v dot n over c. And this is a result of t retarded being dependent on r prime and t retarded being therefore different for different points in the distribution. I like to give you a problem here. Obtain from these formula the potentials for uniformly moving charges, point charges of course. Finally, let me conclude this lecture. We have obtained the scalar and vector potential for a moving point charge for v much less than c. These go over to those results obtained earlier. And we have also understood why physically there is a correction factor. The next lecture we will derive the electric and magnetic fields due to moving charges by taking derivatives of these potentials. Thank you.